All right. So, example number 3, you flip 3 coins. What would an event be? So, obviously, given what we did, you would either have 3 heads, 3 tails. You could have 2 heads and 1 tail, or you can have 2 tails and 1 head. So what would the sample space be? So remember, we need our brace. So we could have heads, 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 tails, tails, tails. We could have 1 head, 2 tails, where the head is first, the head is second, or the head is third. And then we can have 2 heads and a tail, where the tail is first, the tail is second, or the tail is third. And there we go. So, out of these original events, which one of them contain 2 or more outcomes? Well, we can see that the 2 heads and a tail has 3 different outcomes, and the 2 tails and a head has 3 different outcomes. So these would not be simple events, right? They are events, but they are not simple because they contain more than 1 outcome. There's 3 ways of getting both of these options. So then, of course, which one are simple? Well, we can see that the 3 heads and 3 tails. Right? There's only 1 way to get 3 heads, 1 way to get 3 tails. So those are simple events. They're just all heads or all tails. All right. Hopefully that makes a little more sense. All right, let's talk about the probability of rules, or the rules of probability. So, in the following probability rules, we say that this notation, P parentheses E, so it's not P times E. What this means is P is the probability of event E occurring. The probability of event E occurring. So E is going to be an event, right? So 1 or more outcome. P of E is the probability of E occurring. So the probability of an impossible outcome, if it is literally impossible, is 0. Right? Which means that the closer a probability is to 0, the less likely the event will occur. So let's think of some impossible events. Let's say the day after Tuesday is Sunday, right? That's impossible because the day after Tuesday is Wednesday. In Knoxville, so in Knoxville, Tennessee, summer will occur in January. Right? Again, that's impossible. It could be really hot in January, potentially, right? But by definition of summer, that has to be in the summer months, which is like June to August. Good. So these are literally impossible events. These would never happen. Number 2, the probability of a certain event. So this certain means it will happen. It absolutely will happen, is 1, right? It's 100%. Which means the closer a probability is to 1, the more likely the event will occur. So, some certain events would be like the following. The day after Tuesday is Wednesday, right? That always occurs. That's how the calendar works. We could say, if I'm 18 years old, now I'll turn 19 on my birthday. Right? Again, that's just how dates work. Good. All right. Number 3. For any outcome, its probability must be between 0 and 1, right? It's between impossible and certain, inclusive, which means it can be actually 0 or 1. So the mathematical way of writing this, we would say that the probability of the event is between 0 and 1, right? This is how we would write it mathematically, symbolically. So you might see this on some homework. I wouldn't worry too much about it when it comes to a test or anything, but knowing this concept is going to be super helpful. So really, any probability is going to be between 0 and 1, right? So it'll rain today, right? That's some probability between 0 and 1. My parents won the lottery. Something between 0 and 1. If they don't play the lottery, then that would be 0. And if they do play the lottery, then it's going to be between 0 and 1. It'd be really close to 0, right? But it would definitely be somewhere between there. Number 4, the sum. So think about this. What does sum mean? Sum is a fancy word for adding, right? So when you add up all the probabilities of all of the outcomes, it has to equal 1, right? 100%. So again, another way of writing this, if these are all of our events, right, we could write it as the probability of the first event plus the probability of the second event plus the probability of all of the events equals 1. Another way you could write this is using this symbol. So this symbol means sum. So that symbol right there, that just means sum. It's a capital sigma, which is a Greek letter. So you could see this potentially on homework or something. Again, don't super worry about it, especially like on a test or something. But this is what this could also be. The sum of all of the probability is 1. Right? So sum, P is probability, equals 1. All right. Let's talk about a probability model. So a probability model lists out the possible outcomes of a probability experiment and each outcome's probability. So on one side, it'll list out all the outcomes. On the other side, it'll list all of the probabilities of each outcome. So a probability model must satisfy rules 3 and 4 of the rules of probability. So remember, 3 was that all of the probabilities are between 0 and 1. And rule 4 is that the sum, when you add up all the probabilities, they equal 1. Now again, if you need to go back, look at your notes, remember them, right? If you want to read the words for it instead of the symbols, totally okay. As long as you know what those mean, that's all that matters. All right, so problem number 1. So are these tables probability models? So this is going to be in your word problems. So there's a handout for word problems. Make sure you take a look at this. So Ted uses the pickup line to hit on women. Do you have diarrhea? Because you just blew me away. That's one of my favorite pickup lines ever. It is hilarious to me. So the random variable X is the number of girls Ted approaches before encountering one who reacts positively. So is this a probability model? So we have all the outcomes here, and we have the probability of each outcome on the right side. So number 3. Number 3 says that all probabilities are between 0 and 1. Is that true? Yeah, all these probabilities are between 0 and 1. So number 3, we're all good. So let's look at rule number 4. So the sum of all probabilities has to equal 1. Is that true? Well, if we add them all up, what do we end up with? We should get 0.601. Does that equal 1? No. So since it does not equal 1, no, it is not a probability model. So basically what this means is after 5 girls, Ted stopped asking. He didn't like being rejected after 5 women rejected him. So he would just stop. All right, part B. A sociologist randomly selects single adults for different groups of 4. And the random variable X is a number who say the most fun way to flirt is in person. So is this a probability model? Well, if we add up all of them, right, using our number 4 rule, the sum of all the probabilities, do they add up to 1? So when you add up all those, you'll actually see that you do get 1, right? So number 4 is great. Let's look at number 3. Remember we said that the probabilities have to be between 0 and 1. Is that true? Well, no, right? You can't have a negative probability. That doesn't make any sense. So it is not a probability because negative 0.15 is less than 0, right? No, part C. So in a Microsoft Instant Messaging survey, respondents were asked to choose the most fun way to flirt, and the accompanying data is the results. So surveys, probability. So remember, there's only 2 rules to determine if it's a probability model. Number 3 says that the probabilities are all between 0 and 1. Is that true? Yeah, we see all these probabilities are between 0 and 1. Perfect. Let's look at number 4. So remember, rule number 4 says the sum of all the probabilities equals 1. Is that true? So if we add all these up, what we get is 0.99. So you might think, oh, well, that's not equal to 1. So no, but in actuality, yes, this is a probability model. So what we call this right there is called a rounding error. It means that when we rounded it to 3 decimals, this is just what it ended up being. It doesn't mean anybody did anything wrong. That's just what happens sometimes. So if you are rounding to 3 decimals and you get 0.9 or 2 decimals and you get 0.99 or 1.01, we can just say that this is close enough to 1, right? So if you had 4 decimals, right, you could have 0.9999 or you could have 1.0001. That would be okay. That's close enough. Anything more than that would not be. So if you had 0.98 with 2 decimals, that is not close enough to 1. If you had 1.0002, that is not close enough to 1, right? Has to be only one of the smallest decimal points away. Cool. All right. Hopefully that makes sense. Let's move on to unusual events. So an unusual event, is that going to have a high probability of occurring or a low probability of occurring? If it is unusual, would you expect it to occur? Would you expect it probably not to occur? Probably not, right? If it's unusual, probably wouldn't occur that often. So that's going to have a low probability. But the question is, what's a cutoff point? So math always needs a cutoff point. We're not just going to go with our guts and feelings, right? So at what point do we say this is too low? Well, we're just going to say for this class, so maybe a different class will be something different, but for this class, a probability is considered unusual if it is less than 5% or 0.05, right? So if a probability is less than 0.05 or less than 5%, we consider it to be unusual. So let's go back to that problem number 1, right? So we did say that this was not a probability model, but we can still use the probabilities, right? So if we go back to problem number 1, would it be unusual for the first woman who reacts positively to Ted? So remember, the way this works is Ted approaches women and he records the number of women it takes before someone reacts positively. So would it be unusual for the first woman to react positively to Ted? Well, what's the probability of the first woman reacting positively to Ted? We see that the probability of the first woman is 0.001. So since the probability of the first woman is 0.001 and 0.001 is less than 0.05, right? Because we can see if you go from left to right, the zeros are the same. And then we have 0 and 5, right? If we had the same number of decimals, we would see that this is 0.050 and this is 0.001. So 0.050 is more than this, right? So since this is less than 5%, yes, this is unusual. Would it be unusual for the third woman to react positively to TED. So again, the probability of 3, we go down to 3, its probability is 0.105. So how does that relate to 5%? It's more than that, right? So then no, it is considered usual. Which is crazy because that's only 10. But again, in this class, it's 5, we say 0.05. 5% is too much. And we'll talk later in the semester about why that's the case. But for now, 5% or more, too much. Would it be unusual for the 5th woman to react positively? So again, the probability of the 5th woman reacting positively, we go down to 5, over to the probability, so we get 0.242. So again, that's more than 5%, so not unusual. It is usual. Is there any other unusual events given in this table? Well, yeah, right? We can definitely see that this number is less than 0.05, right? 0.02 is less than 0.05. So the second woman would be unusual. So we could say the second woman reacting positively would be unusual, right? Because that probability is less than 5%. All right. So let's talk about rules for computing and interpreting probabilities. So there are 3 of them. The first 2 are the most important, but we'll talk about the last one as well because it is something that we do in everyday life. So first, the empirical rule. The empirical rule is the probability of an event occurring is approximately the number of times the event is observed divided by the total number of repetitions or trials of the experiment. So the big reason why we do the empirical rule is because we have observed something, right? We've done a study. We've actually gone and asked people things, right? There's a survey or a study or an experiment. So another thing we can say, it is the relative frequency of E. So as we said, it's the frequency of E, the number of times E occurs, divided by the number of trials of the experiment. So and this is basically what you already know as probability. So an insurance agent currently insures 182 teenage drivers. Last year, 24 of the teenagers had to file a claim for their auto policy. So again, problem number 2, based on these results, what is the probability that a teenager will file a claim on his or her auto policy each year? So we can see that there are 24 teenagers out of 182 that filed, right? So the number that filed is 24 divided by the total, 182. And when you divide that out, you do 24 divided by 182, you should get 0.132. And that's it. It's as simple as that. So part B, for every 100 insured drivers, we would expect about how many to claim their auto policy? So if this is the probability, right, and we want to know for every 100 people, we can just multiply this probability by 100. And when you do that, you'll get 13.2. So how many people, how many whole people would we expect? Well, if you're around this, right, we would expect 13. All right, problem number 3. A recent Harris Interactive survey of 1,010 adults in the United States showed that 202 of them smoke. Find the probability that a randomly selected adult is a smoker. So remember, we're doing the number of smokers divided by the total number. So the number of smokers is 202. The number of adults was 1,010. And when we divide that out, we get 0.2. So that means for every 100 adults, how many would we expect to smoke? Well, if we multiply this by 100, you'll see that we'll get 20. For every 1,000, how many would we expect? So this time we would do 0.2 times 1,000. And we would get 200. Part D. For every 50 adults, how many would we expect? So this time we would do 0.2 times what? 50 adults. And we get 10. All right. So we're going to start the classical method in the next video, but almost done.